Here in the figure, we see a system of n bodies. And these n bodies have masses m1, m2, mn, respectively. That means their masses can be different. And they are aligned in a straight line and connected by springs. So this each spring has K1, for example, that's for the first spring. It has a constant, right, for the property of the spring. And then we have K1 that is connected to M1. And then after M1, there's a K2 and etc. So this Mn, and that's the last spring, is Kn plus 1. So as you can see, we have n masses, n plus 1 springs. So we want to focus on one mass to see what the equation is like. And by the way, we assume that the motion is to the left or to the right, and the surface is completely smooth. That means there's no friction on the surface. So this n bodies can move freely. So if we look at the first, just to pick one, and then one in the system, let's call it mj. Mj is the mass for the j's body. So this mj times xj's second order derivative. What is xj? Xj is the displacement from its equilibrium. So if this j's body is at the natural position, that means there's no compressed springs on the left or right, then this is at its equilibrium position. So then the xj will be 0. Otherwise, it is non-zero. So this xj is the displacement from its equilibrium position. So it is a function of time. So we want to write the governing equation for the xj. So by the Newton's second law, mass times acceleration equals external force on this body. So that is acceleration, which is the second order derivative of x. So if we use mass times acceleration, which is the second order derivative of xj, equals the external force on this j's body. So how do we calculate? That means the force from the spring on the left, right, and the force from spring on the right. So here we have two portions, this spring on the left and spring on the right. So the force is also depending on how much the spring is compressed or stretched. So this, as we know, it is proportional to the spring constant, right? Kj is determined by the stiffness of that spring, the J's spring. So that spring constant times this two body. You see, these two, if they all moved away from their equilibrium positions, so depending on these two bodies' displacement, so that will determine whether this spring is stretched or compressed, and the magnitude of those. And this sign also indicates the direction that the force from this JS spring on this body. Okay, so then we can see the force from the right side spring is also determined by the displacement of these two bodies. So after we consider the force from springs on both sides of this body, then we get overall force. That is the overall force equals mass times acceleration. So we have one equation for this JS body. How many bodies? And we have total of n bodies. So J, for each body, we have a second order equation. So we have a total of n equations of second order for the n coupled masses. So let's rewrite the system so we can put xj. You see xj has the coefficient negative kj, and also xj has that coefficient negative kj plus 1. And so that's why we have the coefficient negative kj and negative kj plus 1 for this xj. And also we notice for this xj minus 1, that's the displacement of the previous body, right? And it has a coefficient positive kj. And for the displacement of the next body, the coefficient of that displacement is kj plus 1. So that's why when we write the system, rewrite the system, we can organize in this way. So just like combining terms, like terms. So you see a xj, and these two terms can be combined. And we just simply, this equation is written nicely into this form. And we can see each equation involving 3 other displacements, and including itself, right? The displacement of the JS body. Okay, so now we can write the n equations, one for each body. So we have n equations. As you can see, the first equation is m1 times x1 second derivative equals this. And then the second equation will be m2 times x2 second derivative equals 3 terms. And so will be, involving. So we can see that n body will result in n equations. But of course, the first body has a special case because when j is 1, look at this, we know when j is 1, then what is this? There's nobody before this one, right? So that will be 0. When j is n for the last body, so when j is n, the last equation, there's nobody after this last body, so this part will be 0. So we have 2 special cases. That means first equation and the last equation of the system. They are okay, so special case. But anyway, we see that the system is in this form. So it's a tridiagonal matrix B, such that x second order derivative equals the tridiagonal matrix B times X. And this is mass. So this matrix with the diagonal entries being the mass of each object. And so the diagonal matrix can be easily inverted. So we just see this form. See, it's just diagonal matrix M times X, which is a vector. This is a vector X, second order derivative. So the X vector, and then we can write the matrix in this form. So after we write the matrix in this form, and we can write X second derivative and leave it on one side. So M inverse times B. And overall, this is just the matrix. So that is what matrix it is. We can call it A, just a matrix. So we write it into a simple form, which is some matrix, right? Let's call it A, X. So now, so it's simply a second order system of n equations with this matrix A here. A is determined by masses of n bodies and also the spring constants of the n plus 1 springs, because the B matrix has something to do with the spring constants. So the system is all determined. It is a second order system of equations, n equations. So now with this second order of n equations, we want to reduce to first order system. So quickly, if we define a velocity vector, which is see, derivative of the displacement, then the second order derivative of displacement is just the first derivative of velocity. So this can be written as velocity equals ax. So you see this becomes first order as soon as we define a velocity vector. So now that is becoming, so by introducing a velocity vector, which is the first derivative of displacement vector, then the second order derivative of the displacement can be replaced as first derivative of the velocity. Okay, so that is our original equation. Remember, that's x second derivative. So now it's becoming first order. So we have v prime equals ax. Now overall system is larger because originally we have just a system of n equations. Right now we have n plus n. We have a system that is twice as many equations. So now we can write the system in this form. As you can see, this left side is just the derivative of a vector, right? So that's derivative of a vector, xv. And the right-hand side is a matrix times xv, the vector. So the matrix in block-wise, so this each block is n by n. n by n. So this is a large square matrix, which is 2n by 2n for the n-body problem. Yeah, so this is easy to see because this V, as you can see, it's a 0 times x, right? 0 matrix times x plus V. That's why this is a 0 times x identity times V. So that's the first equation. And the second equation, A times x plus 0 times V. So that's A times x plus 0 times V. Yeah, the second equation. So we can see that the new system is written as first order. So for the first order, we know we can use real complex eigenbasis theorems to solve the system. So in order to give you a concrete example, I will consider a two coupled masses. So yeah, two coupled masses. That is, we have two masses with some assumption to make it simple. Each mass is just one. So they are having the same mass, which is one. And the three springs have the same spring constant, also one. They all have the same stiffness. That means they have the same spring constant, the three springs. So in that system, if we go back to look at the picture, you can quickly see that, right, as a result. So each equation, so this is the system. So if it's 1, 1 plus 1 will be 2, so -2 along the diagonal. So it's a -2, -2. And non-diagonal entry will be 1 and 1. So for a system of two masses, then we have only this portion. So it's a very small system. Yeah, for this is a special case. And also, if each mass is 1, so M1, M2, so this will be 1 and 1. So just reduce to just identity matrix, 2 by 2 identity matrix, you see. So that will be a very simple situation. Then we can quickly write the system. Coupled masses will be a system of two equations of second order. The first mass has the displacement x1, second mass has displacement x2. They're both functions of t, so this is a vector x1, x2 that satisfies this second order equation. So now we want to reduce second order to the first order. So by defining a velocity vector, so we know that x derivative is equal to velocity. And so from here, you can see x derivative is equal to this times velocity, right? So that's velocity. And then velocity's derivative is equal to this times x. Yeah, so we can see the system, according to our previous discussion, it's reduced to the first order system. But the system is, instead of two equations, we have four now, four equations, and also more variables. In addition to the known displacement functions for each mass, we also have velocity, unknown velocity of each mass. So now a two-body problem becomes a system of 4 equations of first order. And then if you want to find eigenvalue and eigenvectors of this matrix, this is our matrix, this bigger matrix, let's call it K. In order to find the eigenvalue eigenvectors, we just use this matrix K and find the characteristic polynomial equation of lambda, then we can solve this for lambda to find eigenvalues. So this matrix, find eigenvalues, then we can get lambda is plus or minus I. This is a complex eigenvalue, right? You have 2, because for this real matrix, we know that we will have complex conjugates. Like as once you have one complex eigenvalue, you have its conjugate as also a complex eigenvalue. So plus square root 3i or minus square root of 3i. So okay, we have a total of 4 eigenvalues. But we only choose this for each pair, we just choose 1. For this pair of conjugate complex eigenvalues, we pick a positive I. For this pair, we pick just the positive square root 3i. And then we can find first, when it's I, when it's negative 3i. So let's say for this one, for the other one, we can find the corresponding eigenvectors. And for eigenvalue, we find the corresponding eigenvectors. So for lambda 1, we find eigenvector v1. For lambda 2, we find its corresponding eigenvector v2. But from v1, we can split, because it's complex eigenvector, then we can write respectively the real part and imaginary part, right? You see real part is just the 1, 1, 0, 0. Imaginary part is 0, 0, 1, 1 times I. Yeah, so we can write that in the complex eigenbasis theorem we call U1, W1 respectively. So that's our notation, right, for the real imaginary part of the V1 eigenvector. And for V2, which is also a complex eigenvector, so its real part is just the 1, negative 1, 0, 0. And its imaginary part is the I times 0, 0 square root of 3, negative square root of 3. So then we call the, just write into 2 parts. Then we can see immediately the real part times I, plus I times the imaginary part. So now we have U2, W2. So according to the complex eigenbasis theorem, we write a solution. Remember, this Z is that first order system, Z prime equals KZ, right? So if we look at this system, we can write it Z, which is this part, this Z. Z first derivative equals the matrix K times Z. Yeah, so for this Z, once we solve it, we will find x1, x2, v1, v2. Those are the velocity vectors. So, although I use the same notation, but don't mix this V1, V2. So we can take this out just for you to not confuse with the previous V1, V2, because those are the velocity of each mass, right? So be very clear about notations. So so now let's just remove those, the use of same notation. So I don't need that V1, V2 because I can, after splitting that eigenvector into real part, imaginary part, that's the part I need, right? This is the real imaginary part of that eigenvector corresponding to this eigenvalue. And this is the real and imaginary part of the eigenvector corresponding to the other eigenvalue. But they are conjugate, the eigenvalue eigenvectors we don't need to use. We know by the theorem we already have enough information to represent a solution for this first order. So here is the representation. Recall that in the representation formula, we have e to the something, right? E to the real part of the eigenvalue. But here in the real part is 0 times t. Why? Because if you look at the eigenvalue, do we have a real part? Real part is 0, right? This one also, real part is 0. So that's why we represent, because we have only the 0 real part for each eigenvalue. So e to the 0t, which is 1. So we don't need that. So similarly, for the other part, we also have, because the real part is 0, so that is 1 simply. So it makes the solution look like this. Okay, so now do we realize this part is due to the eigenvalue and eigenvector here? And this part is due to the other eigenvalue and eigenvector here, real and imaginary part. So we can represent the z, which is the solution of the system, first order system, in this form. But remember, K1, H1, K2, H2 are arbitrary constants. So we need to, for example, determine the K1, H1, K2, H2 in this, see K1, H1, here's H1, K1, negative sign here, K2, H2, H2, negative K2. So that's the form of the solution. But what should be the K1, H1? They can be anything, unless you want the solution to satisfy a certain initial data. For example, if z at 0, because if we require when time is 0, they should satisfy an initial condition. Then you will need to determine, right? You can have enough information to determine K1, H1 or K2, H2. So how? All you need is to substitute the t being 0 in here. So when t is 0, immediately sine t, this is 0. 0 times anything will be 0. Sine t will be 0, right? When t is 0. Everything will be gone except, well, cosine 0 is 1. Cosine, so then you only have this part and this part. That's why I put K1 U1 plus K2 U2 H2 W2. So these two parts I put together make it equal to C. That's the initial data. So then we have a system to solve. Yeah, so this Z is a general solution, right? That's the form of any solution. But if you have initial data, you will be able to determine a particular solution that will satisfy initial data. So once we solve the system, so this system realize the system is I put the 4 columns. This is the, remember the real part of that first eigenvector, imaginary part of the first eigenvector. I put them first column, second column, third column, fourth column, right? So the real part, imaginary part of the second eigenvector. So we just put into the matrix of 4 columns. Yeah, it is 4 by 4 matrix. 4 by 4 matrix. Then those numbers, those coefficients of each column, you see, can be written here as entries of this solution vector to be determined. K1, H1, K2, H2. And initial data already provided. So all we need is to solve the system for this vector. So this is to be solved. Yeah. So yeah, we already know all this, right? So we can have this matrix times this column vector, this vector highlighted in yellow is the vector to be solved. Then once we find K1, H1, K2, H2, then we find a particular solution. Yeah. So the particular solution is with the found K1, H1, K2, H2. You put here those numbers you found based on the initial data. Then you get a particular solution that satisfies not only the system, but also the initial data. Okay, now I want to look at the original problem for a second. Original problem was only a system involving x, right? Has nothing to do with velocity. So that was the problem we were looking at. Although we reduced it to a first order involving velocity. But then if we go back to the original problem, can we answer that problem? Sure, we can, based on our the x. If we look at the w, you realize the w has 0 entries, right? W1 or W2, the first 2 entries are only zeros. They will not contribute to the solution vector x1, x2, because our solution vector is in this form. So this W1, W2 will not, yeah, so we can simply, in our general solution, if our interest is to find x, then what we can do is, in this general solution formula, if our goal is not to worry about velocity at all, then we can simply write our x by taking out those w's, w1, w2 terms. Yeah, so that means we can just focus on the u1, u2. Yeah, so that will those terms involving U1, U2 that will contribute X, right? Contribute to the X vector. So let's write our X vector, but because we can combine, you see the U1, U2, right? So U1, if you remember what U1 is, U1 is a vector of 4 entries. U1 is vector of 4 entries. That's the U1, the real part of the eigenvector. But the first 2 entries, 1, 1. U2, right, is the real part. But we only look at the first 2 entries will be 1, -1. Okay, so that is just for your observation. So 1, -1. So let's extract only the top 2 vectors, 1, 1 or 1, -1, because we right now with the focus on the X only. So let's go ahead, write our, so instead of the Z, the vector of 4 entries, I want to write just the X, the vector of the first 2 entries of Z. In that case, we really can drop the W vectors, right? Keep only the U1, U2 vectors, all the terms involving U1, U2. So that's what we have now here. So this V1 is actually the vector U1 truncated after I ignore the next 2 entries, 0, 0 entries. Right, this V2, as you can see, this V2 is actually the U2. U2 was this, the real part of the other eigenvector, right? So we just use only the top portion. So here, these 2 vectors, as I pointed out, these 2 vectors are called normal mode vectors of the coupled mass system. Normal mode vectors. And so they can be used to represent the X solutions. Yeah, so just right now, so this notation, I want to use it. Although I use V1, these 2 are vectors, they are, yeah, so it's actually from the real part of those 2 eigenvectors, remember? So we call them, we only keep the top 2 entries, and these 2 entries will contribute to the X1, X2. So here we have a general solution for X. And general solution for X is in terms of these 2 vectors, and these 2 vectors are called normal mode vectors of the coupled mass system. And we have those numbers. You see, this is a 1, right? 1, although was not necessary to be included, the sine t, cosine t. And this is, but I just want to point out that the 1 is there. And square root 3, right? Cosine square root 3, sine square root 3t. So these 2 numbers are called the normal frequencies of vibration. So you see, general vibration is composed by 2 frequencies. So it's a superposition of different frequencies of vibration. So either this frequency or the other frequency of square root of 3. So by looking at the general solution, and we recognize solution of the system have two normal frequencies, and also so superposition using the normal mode vectors. And then I want to even simplify it a little further. That is, we suppose the two masses are initially displaced from equilibrium positions and released with no initial velocities. So when they're displaced, and they will start to move and to vibrate, right, left and right, the two bodies, but without initial velocity. With that assumption, that can further reduce our system, because when we have no initial velocity for the two bodies, that will lead to H1 being 0, H2 being 0. So the solution will be reduced to only the cosine term, K1 cosine t times the vector V1, K2 cosine square root 3t times the other vector V2. So that is based on the assumption of initial velocity being 0, then we can get a solution of this form. And this 2, we call this one eta 1 t, and that's a eta 2 t. And as you can see, and this is a superposition of eta 1 and eta 2. That means as soon as we look at any motion of this with that assumption, so any motion with this assumption, if the two masses are initially displaced from equilibrium, but released with no initial velocities, and then our general solution formula, that means the motion solution formula for this x will have no such a term left. So you will have a very simple solution formula. So then we will have with this, then we have the motion that is given by a superposition of these two eta 1 and eta 2 functions. So eta 1 is called a normal mode. Eta 2 is another normal mode. So as you can see, we have two normal modes that can generate any motions of this kind of system. So this is a definition for normal mode. And basically, that means any more complex motion can be written as a superposition of these two normal modes. Okay, so with this discussion, hopefully you see the general analysis method. And then if you imagine, if you are given a system of 3 coupled masses, what will be the difference? So you can think about a slightly larger system and then think the whole process. Of course, when you have a system of 3 bodies, then you will have x1, x2, x3, right? Your velocity will be v1, v2, v3. And certainly the first order will be involving a matrix of 6 by 6. So this will be a 6. So the A will be 3 by 3, but this matrix will be 6 by 6 for the first order system. And yeah, from 2 coupled to 3 coupled masses, then you have slightly larger system. But of course, when you look for the eigenvalues and eigenvectors, you should use some software, for example, MATLAB, to calculate eigenvalues and their corresponding eigenvectors. Okay, so after you find the eigenvalue and eigenvectors for the first order system, that means for the K, the matrix in the first order system, and then you are ready to represent general solutions. And afterwards, you also think about what should be the normal mode. Normal mode, then you think of the X part only. Can you possibly write the X into a superposition of 3 motions? Yeah. So if you can, so that you see this is the one normal mode, the other normal mode, and then for the 3 coupled masses, you will have a third normal mode. Then you will have 3 normal modes, and any motion that is caused by the initially displaced from equilibrium, right? The masses are initially displaced from equilibrium and released with 0 velocity, 0 initial velocity. Those kind of motion will be given as a superposition of the 3 normal modes. Yeah. So that is the case when you have 3 coupled masses. Okay.